All right, good evening, everybody. I'd like to introduce you to Professor Roger Deane. I asked him just now, when I Googled him, I found UCT, Pretoria, Wits, but he's got a Wits email. There's, no, he's not Wits, he's at UCT, but he's got this group. I'll leave it to him to explain. It's complicated for me. So it looks like he's at every university in the country, just about, so with some way or another. He's got students and postdocs and whatever at every university that he's been after. So I'll leave it to you.
Thanks very much, Derek, and welcome everyone on a chilly evening. I appreciate you coming out. And of course, you're all staying up till 3 o'clock tonight to watch the final play. So it's an especially long day, and I'm really, really appreciative of you coming out. Derek's right. I've been at many South African universities, but in the last 6 months, returned what feels like home to Cape Town. My wife is from Cape Town, born and bred, and I spent all my life in Cape Town. So I've sojourned via Rhodes University, University of Pretoria, Wits, but now feel very much at home. Hermanus is also very familiar to me. My wife's family on her mom's side has been holidaying here for the last almost a century, probably, originally from Worcester roots and then Cape Town. So I've been coming here at least once a year for the last, well, since I've known my wife, which is a good 25 years. Yeah.
So I have a question from the bachelor. That bucket, is that to scale in relation to the dishes?
Roughly, yeah. So
it gives you an idea.
Yeah, so these are supposed to be 13.5 meter dishes, and these are 15 meters. So it's like a 10-story building. Yeah, so it's good to be here. I'm going to talk about this remarkable telescope. You're seeing a few telescopes in here. There's the MeerKAT telescope, and then I'm going to be focused on the dish, the big dishes, these 3-story dishes, rather than these wires, simpler antennas on the right-hand side. And that's what's hosted in Africa, and there's an ambition to spread this beyond South Africa into the rest of Africa. I'll tell you a little bit about why it's a giant eye. And yeah, I think the eye is pretty obvious, but there's a listening component to this as well. And then I'll talk a little bit about the science goals, but I want to start with something you're a lot more familiar with than, what is a radio telescope? You've all sat around the campfire under our beautiful southern skies, bushveld setting, and seen our beautiful southern skies. Southern skies are very relevant because, of course, our Milky Way, the center of our galaxy, lies in the views from the southern hemisphere, a lot more easily viewed. And you see this band of stars, which, the analogy I often use is that we live in a kind of outskirts of a fried egg in the middle of the white. And the center of the galaxy is in the egg yolk right in the middle. And our view in the sky, we're embedded in this, and we see, the egg white in the middle. There are still stars around us, but sort of this plane of the Milky Way. That's what our eyes can see. What we're seeing there predominantly are stars with temperatures of order 5,000 degrees Celsius, like the pretty average star, which is our sun. Now, people have been looking at that view for thousands of years, millennia, for thousands and thousands of years, and the views used to be better because pollution and things. But still, telescopes have transformed our understanding of what those things are and what, in fact, is out in the universe. Go back to Galileo Galilei, the first to make scientific use of a telescope. He didn't invent a telescope. That was a Dutch scientist. Galileo was the first to obviously point the telescope at Jupiter and see its moons, see the phases upon Venus, and obviously challenge the Copernican principle that we lie at the center of the universe. So telescopes have completely transformed our view, and what the next step was actually spacecraft that have traveled out to these planets and given us exquisite views of so there you see those 4 moons that Galileo resolved for the first time, but in flybys from spacecraft. A little bit.
Yeah.
Okay, I'll go a little bit louder. A key thing that I always emphasize is those planets are orbiting around a sun, our sun, which is an average star. I like this because it sort of illustrates that is very much a dynamic body. It's not just the static sun that's either covered by cloud or not. It's this very energetic process that is going on and spinning in its own right. And one of those average stars, like our sun, is born at some point. Our sun was born about 10 billion years ago. And the James Webb Space Telescope, which I'm sure you've seen extraordinary images of, you can recognize that by the shape of these spikes around some of the bright stars. I can't point, but towards the top of the image, if you look at the bright stars, there's these typical spokes. You can think of that as a sort of a fingerprint of some of the mirror configuration and the strut configuration in the JWST. But more importantly, what you see in the foreground are dust clouds, and you see some bright stars that are just in the process of forming. And our sun, just one, like many suns in our galaxy, formed in this kind of stellar nursery. And it's difficult to really appreciate how many of these average suns there are. This is a view of a nearby galaxy, which we're going to stream across and then zoom out. But this is just giving you a sense of the enormity of just in one galaxy, how many of these average stars, each of which we expect.
Red button. I don't know if that shows anything.
It probably won't
No, it
reflect
doesn't
on
show.
the. Yeah,
It's not
sadly.
easy. No. Right.
Thanks, though. You know, this just keeps going and keeps going and keeps going, like grains of sand, you know, on the beach. And that is just one galaxy of hundreds of billions in our universe. It's extraordinary how average yet special we are, orbiting our little average sun on the outskirts of a fried egg. You know, when we look back around the campfire and ponder what those stars are. So this is a little bit more sophisticated than a fried egg analogy. This is kind of the best model we have using data of what our Milky Way galaxy may look like if we were to step out of it and look down. So the fried egg analogy, you've got the yolk towards the middle, you've got these beautiful spiral arms. We lie sort of in suburbia, about 2/3 of the way out. If you might be able to spot the small Earth there. And that's sort of what shapes our view of this. But it's important to remember that is an average galaxy, and there are hundreds upon billions of those within our universe. This image is one of the deepest images ever taken with the Hubble Space Telescope. It's called the Hubble Ultra Deep Field. Hubble, it was a novel idea. At the time, astronomy, and I'm talking sort of early 90s, 1991, 1992, astronomers used to look at specific objects by and large, or do very wide surveys of sort of the whole sky. What the director of the Hubble Space Telescope, the first Hubble director of the Hubble Space Telescope, Bob Williams, did was he said, let's use the discretionary time that I have, which is a real thing. Directors get 5% discretionary time, which they allocate to strategic projects. And he said, let's stare at a blank patch of sky. And so if you took a shallow image of this, you wouldn't really see much. There'd be a handful of stars and maybe 1 or 2 galaxies. But what Hubble did was it stared for 11 days at one blank patch of sky, sort of insignificant, picked fairly at random. I mean, they didn't choose a bright location, but it's a pretty random location. And what they revealed were just thousands upon thousands of galaxies of the most distant galaxies. And I'll talk to you in a little bit about why that is. There are actually only about 3 stars in our own galaxy that are in this photograph. The rest are all distant smudges in the far universe. And, you know, the James Webb Space Telescope, the successor to Hubble, went up and did a similar thing, stared very deeply for a long period of time with its enhanced power. And it's discovered some of the most distant galaxies in the universe that are known. And this is actually quite an outdated slide. This is 13.3 billion light years away. The universe is estimated to be about 13.8 billion years old. So this is looking at it at the birth of very much within the first 500 million years of our universe. And there are more distant galaxies that have been discovered since. I need to update this with the latest that has come out. So, you look at these stars and you look at these distant galaxies and you quickly realize that astronomy is, and telescopes are time machines. They allow you to see very, very, very far back in time. So don't worry about the labels here too much. Start at the left-hand side and you see what is effectively our model of the Big Bang, how the universe started as a very hot fireball. It gradually cooled and eventually got to a phase we call the Dark Ages. It had cooled because it had expanded, but the stars hadn't been ignited yet. And then suddenly those first stars and galaxies and black holes that form start to shine. I'll get to why black holes shine in a moment. But it's that point that James Webb Space Telescope is capturing those earliest galaxies that are essentially lighting up the universe from the start. And they are so distant. If you compare, this is a beam of light bouncing back and forth like a ping pong ball between the Earth and the Moon, and that's how long it takes. Roughly 1.3 seconds or light seconds. Light traveling at 300,000 kilometers a second, beam to the Moon, gets them in roughly that period. So a lot faster than the Artemis crew that recently visited there again for the first time in 50 years. And so on the scale of the universe, 13.8 billion years look back time with the birth of the universe, that's actually incredibly slow. And so what it means is when we point our telescope and we look at a make a deep image of the universe, some of the light that is landing on that telescope has traveled for billions upon billions of years. And we're able to, through this process, trace the history of galaxies as we step through that deep image. It's almost like taking a deep photograph, and the longer you expose, the more you're seeing, people in their teenage years, in their baby years, while in the foreground you have in their later years. And so we were able to kind of study the history of the universe. And one of the things we've learned is that feeding black holes, and the simulation is trying to give you a sense of what's going on there. There's a black hole in the center, but there's very, very hot gas falling into it. And there's a semblance of some jets that are being spewed out because of twisting of magnetic fields. What we've learned with deep images that have, taken this time machine approach is that back in the heyday of the universe, about 3 to 4 billion years after the Big Bang, this was prolific. Most black holes were actively feeding material, and there are all sorts of reasons as to why that is. But that has had a profound impact. These black holes and their feeding habits have had a profound impact on the evolution of galaxies, including our own. So one thing that's been quite phenomenal in the amazing acceleration of computational power that we have in the average device, but also in data centers that now astronomers have access to, is we're actually able to simulate the universe, create the rules of the universe in a box, in a computer, and if you give it enough power, you add enough particles, and you put in reasonably appropriate rules of gravity and of how matter interacts when it's heated, you can actually simulate the universe on the largest scales. And this is what that is. What you're seeing here are on scales of billions upon billions of light years across. And so those fibers that almost look like nervous tissue connecting are actually thousands upon millions of galaxies that are interconnected in this, what we call the cosmic web. This is what galaxies look like on the largest possible scales, if you could zoom out. And we're able to recreate this in our computers and compare how well we think we understand certain physics with what the observations tells us. And that's a fundamental test that we have to do. And one of the big drivers about why we want to survey larger and larger patches of the universe, as well as the combined with these deep, deep patches. And so what you're seeing here are the effects of those accreting black holes spewing heat and energetic particles into the universe, and they fundamentally shape the environment. A bit like having maybe a loud neighbor with loudspeakers. So another fundamental thing that's changed, in the last few decades, but increasingly so in this last decade, is the need to look at the universe with all the possible information that we can glean. And our eyes are limited just to that small visible band, wavelengths of light of order 500 nanometers, a few hundred billionths of a meter. Whereas, you know that you can put night vision goggles on and you're able to see things that your eyes cannot see. You get sunburn from ultraviolet rays, that you can get an X-ray and that can show your bones. So in a similar way, in astronomy, we have to use as many different wavelengths as possible across the electromagnetic spectrum in order to study these exotic phenomena in the far off and nearby universe. So X-rays are very important for studying black holes. Infrared is very important for studying star formation, and radio is incredibly important for both of those things and many others. Now, some of these observatories are up in the sky, but the radio telescopes I'm going to talk about are here on Earth because they're just too big to launch. And the first radio telescope was built by a radio engineer called Karl Jansky. He was trying to understand radio interference affecting long-distance communication systems down in the early 30s, late 20s. And he built this back in 1933 in this Bell Laboratories in New Jersey, where so much amazing innovation has happened. If you zoom in there, that wheel is from the Ford T model. That's how he was rotating his simple antenna. And he was the first to discover some radio emission towards the center of our galaxy. That sort of gives you the scale there as well. So essentially, his map of the universe, these contours of intensity that you see on the top there, he actually didn't make that. It was made later on, but that's from his data. And he showed that there's a line there that's kind of the thick black line is cutting things off, but that's because he was in the northern hemisphere. You couldn't see our southern sky from where he was. But what you can see in the color is a later map, which maps the whole sky. And you can see he was just seeing towards the center of our Milky Way. He was seeing brighter, 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 but then he hit the horizon because of where he was in New Jersey. Now, the New York Times noted this event, and as is often the case in our field, they very quickly turned to aliens. And in the New York Times article, short article, this is the birth of of radio astronomy and of multi-wavelength astronomy. There is no indication of any kind that these results are the form of some intelligence striving for intergalactic communication. Very important to note in the article. I'll come back to the New York Times reporting radio astronomy results later. So I've told you that we try and look at things different wavelengths to see different things. Like you can see your leg through your eyes, but you can also use an X-ray to see the bone beneath. Now, this is an example of a very massive galaxy. What you're looking there are a whole lot of stars, much larger than our own Milky Way. It's quite an old galaxy. It's red and sort of lost all its gas, and there's no real ongoing star formation. But if we turn on our radio glasses, what you see is something completely different. At the same scale, transition into, this is radio, this is plasma that has been shot out from the center. If the zoom will excuse me for a moment, there's a black hole that lies in the center there. And previously there were jets that were stemming from the center of that massive galaxy, because at its center lurks a supermassive black hole about 1 billion times the mass of our sun. And that was shooting out electrons at close to the speed of light. And what you can see is these orange lobes are well beyond the galaxy. The thing you could see, I mean, they used to live inside that. They were accelerated out by that black hole and twisting magnetic fields. So it's a fundamentally different view of a fundamentally different physical phenomenon than you see with a simple optical telescope. Well, not a simple, just an optical telescope. And so this shows that you need to augment your views of the universe to see the full picture using at least 2 telescopes, as is becoming the standard these days, as many as you can. So MeerKAT is playing a fundamentally important part as part of this growing, multi-wavelength view of the universe, and what I'll get to later in multi-messenger. This is a photograph I took with my phone, taking off from the inauguration of MeerKAT back in 2018. If you look towards the center there, you have these 3-story building antennas spread across the Karoo. They are clustered in the center, as you can see. There are 64 of them. 2/3 of those lie in that central kilometer, and then the others are spread out to with about 8-kilometer separations being the maximum. How that's spread out is very, very important. Maybe we'll get into it in the Q&A. But there's 64 of these, and the sharpness of the image, the level of detail that you can see if you make an image with this telescope. I say image because it's not a typical image like if you take out your phone and take a photograph using a CCD. But we can maybe get into that later on. The sharpness of that image is about 1%. If you look at the moon, which is roughly the size, as most of you will know, of your thumb at arm's length, it's about 100th of that, the level of detail you can see. So not as good as Hubble Space Telescope, but extremely good for this kind of telescope. That telescope lies in a protected zone. There was very careful site selection to find the optimal site, not only for MeerKAT, but for the larger bit of what's called the Square Kilometre Array Observatory. So it's protected by an act of parliament. And as you may see in the press when you hear about MeerKAT, is that it's a big data machine. It's spewing out a lot of data, and we have to handle that. So let me just tell you briefly why that is. The way to think about this telescope is not individual antennas, actually. It's about pairs of antennas, what we call baselines. So just think of handshakes. If we all had to get up now and make sure that we all shake each other's hands at least once, MeerKAT is doing that, but doing that on the time scale of microseconds. And it's making a measurement for every handshake, and there are lots of handshakes. If we all had to shake each other's hands, if there's 64 of us in the room, as there are MeerKAT antennas, there'd be 2,000 handshakes every few microseconds. And for the SKA Mid, this will expand significantly. So this is why it's a big data machine, and that's why you fill up lots of disks. This laptop has a terabyte of storage. This would be filled up every hour. This is a high-end laptop. So it's a big deal. I won't go into detail here, but other than just to say, it's not a point-and-shoot facility, unfortunately. You don't just take out the MeerKAT, grab a shot, and you're good to go. There's unfortunately a ton of data processing that needs to happen. Anyone here who's been in a technical field would have heard about may have heard about a Fourier transform. It's an abstract mathematical step within which we make the measurement, and then we have to create the image. So there's a perfect image I took of a building in the University of Pretoria. Here's an abstract mathematical representation. What the MeerKAT does is it measures those circles, small slivers of the abstract mathematical representation of the perfect image, and then we try and recreate the grainy thing at the bottom left. That's what we do. And it's very different to taking the original photograph. So let me use an analogy. It's as if you're trying to play music, but the notes have been blurred, your view of the notes. So you make mistakes. Things are slightly off, but you can get the general melody. And the more and more you sharpen your image, the more you are able to unblur this view of the sheet music, the better you can create the intended melody. And that's what we're trying to create with the MeerKAT telescope. Okay, I need to tell you about radio color. So if our eyes can see color, what is the equivalent in the X-rays or in the radio? It's just a differing intensity in the different filters. So you see some beautiful colors in these merging galaxies. If you split those out, there are different filters which capture different things. If you look carefully, the RGB, red, blue, green, and blue, are slightly different. And that's because dust is more prevalent in some, hot stars are more prevalent in the blue. And if you combine them, you see the collective color. We do the same in the radio. Caveat is MeerKAT does that for 32,000 channels. So in addition to all the handshakes around the room, all these radio channels creating radio color are another reason why we have a ton of data. I won't go into detail to the site. Essentially, for the SKA, we'll need about 1 billion CDs per year to store the data. And effectively, if you stack those CDs together, it would be from a minus to Pretoria, just to give you a sense. And as I said, filling up one of these laptops every hour with a terabyte of data. So we have this challenge, this big data challenge. And we also have the challenge that the theoretical models that we compare our data to, remember I spoke about recreating the universe in a computer, they are becoming more and more complex. So the algorithms that we use to compare data to theoretical model are having to get smarter and smarter. And AI, artificial intelligence, is becoming a bigger and bigger thing. You have to ask, is the data volume worth it? Sounds all impressive, but why go through the effort? Why build the fast computers to do it? And the answer is just with a sheet music where you need to have as clear a view to reproduce as harmonious a melody at the end. Here, to have as clear a view of the beautiful tapestry of the universe, you need as many antennas, and you do need all that data to recreate these beautiful images. This is the inauguration image that MeerKAT released of the center of our galaxy, and this transformed our view of our Milky Way galaxy through radio eyes. It was startling how well it worked and how beautiful and scientifically rich these images that came out through. This was not just publicity. The first paper from MeerKAT data was published in Nature, which is the most esteemed scientific journal in the world, and it was on this topic. And you can see all sorts of things. One thing you can surmise is that the galactic center is not quite like suburbia. There is a lot of energetic phenomena going on. There's an accreting supermassive black holes. There are these filaments that are many light years in size and very thin, which MeerKAT discovered hundreds of these, and they're exploding stars. This just was a complete delight to astronomers that focus in on this field, and astronomers anyway. And to give you a sense of the scale of that on the sky, remember the thumb at a distance, that gives you a sense of the scale of this image. I previously spoke about the Event Horizon Telescope. Right at the heart of that, in 2022, we were able to capture the image of the black hole that lies right in the center. And there's a dim spot in the middle there because the black hole itself bends the light around and it captures light. That is tiny compared to this, but it lies right in the heart of that. President Ramaphosa used this as a backdrop with President Xi's state visit. We know that he doesn't just appear in any photograph. He's quite selective. But to give you a sense of it on the sky, if you look at that sort of band, we're sitting in the fried egg, the radio eye version is right in the heart there, and it's unobscured by dust, which the Milky Way is. Again, feature a radio image featuring on the New York Times, this one a little bit prettier than Carl Jansky's back in 1933. But just to give you a sense of the impact that the MeerKAT telescope is making. This is not the only time that the New York Times has featured a MeerKAT image. And in fact, there are art galleries around the world that feature some of the MeerKAT's images. So if you contrast Jansky's original image and you look at the blue circle there, that's the heart of where this is. You can see the New York Times article there, MeerKAT's image of that, and then the Event Horizon Telescope, which is 5 billion times better sharpness of the image, the angular resolution than Jansky's original map with that first radio telescope using 4T wheels. So we have moved along since Jansky. Right, so let me talk about the Square Kilometre Array Observatory. Two technologies, as I said, the dishes on the left and the simpler antennas on the right, and the dishes being located in South Africa. This is a huge international endeavor, a multi-billion-dollar project. It's been going on for multiple decades. This really will be probably one of the largest scientific infrastructures on the planet, located here in South Africa. But with partners across the world, and you can kind of get a sense of who's involved there. Observatories of this kind need to, address a large swath of the community's interests, scientific interests. So some of the key scientific drivers are testing gravity, yes, looking for signs of extraterrestrial intelligence, exploration of the unknown, but everything in between, from understanding how those first galaxies formed and how those black holes started accreting, how they evolved to today, understanding this mysterious dark matter, understanding how magnetic fields arise in the universe and how they evolve. So a huge range of science across that huge cosmic range of time. A key thing that we want to understand is actually counterintuitively the dark ages. How do you see the dark ages? Well, it turns out you can use radio telescopes to actually start to see in the early universe. So what the simulation is going to show you is a Swiss cheese-like view of the universe. The holes in the Swiss cheese are essentially the stars heating up cold gas. And you start to see gaps between the cold and the warmer gas. And it turns out these very simple radio telescope design that is going to be built in Australia, is being built in Australia, should be able to uncover this movie as the cheese becomes more Swiss cheese-like. And then another key thing that we're doing with these radio telescopes, and will be a key focus of the dishes here in South Africa. These are two galaxies merging, and at the center of them, as I said, lie supermassive black holes. And these things find each other. So this does a cosmic dance, and as it does that cosmic dance, slowly those black holes will eventually find each other. Amplified the size there just so you could find them on the screen. But these black holes are very, very massive. As I said, about 1 billion times the mass of the sun, squeezed inside the size of a solar system. They find each other. And when they do that, you start to see, this is coming to the hearing, or the big ear of the MeerKAT. You start to generate what are known as gravitational waves, disturbances in space-time that propagate out like ripples in the universe. And what the MeerKAT can do is it can actually hear these. It's a crunching up of space-time that's described with what's called gravitational waves. And if a gravitational wave passed through here, it would make me taller and thinner, and then shorter and fatter. Taller and thinner, shorter and fatter. That would be the oscillation that happens. But it requires very, very massive distortions to space-time to do this. So it's not just going to be a drop of water hitting a pond. It's got to be the biggest hammer you've ever seen hitting, very, very turgid steel. How do we do that? How do we detect that? Sorry, there's another concept here. These are these rapidly spinning neutron stars called pulsars. They turn out to be the most accurate clocks in the universe, and we detect them with radio telescopes. And a radio telescope like MeerKAT can detect 50 million rotations per day of the fastest pulsar. So what that means is you get a lighthouse-like effect 50 million times a day. What that means is you can have the most accurate Swiss clock that you could ever imagine, and it's thanks to these city-sized neutron stars in our galaxy that we use as GPS in a similar way to which I use Google Maps to get here today. It's using relative timing. So these are the most accurate natural clocks in the universe. And if you have them spread across the sky, you can use them in an analogy, in a way analogous to GPS, how we use GPS satellites on Earth. And you can map out these gravitational wave disturbances coming across the Earth. And that is a fundamental experiment testing the nature of gravity. We also connect MeerKAT to telescopes around the world. And so you're seeing these lines or these baselines to other telescopes elsewhere. And that is a key technique in which we make, for example, the images to of the supermassive black hole. MeerKAT won't be able to participate in that experiment. It doesn't observe light at a high enough frequency, but it will connect to global networks in this way and perform some very important experiments in this manner. Of course, a key question is, are we alone? And this is something that's also on the menu of things that are attempting to be tackled with MeerKAT and with the Square Kilometre Array Observatory. And we do what's called a techno-signature search. Very simple. If you somehow traveled 50 light years away, what experiment would you do to try and detect if there was artificial life or there was intelligent life on Earth? I know there are definitely lots of jokes that could be told at the end of that, but you would look for things that look a bit like noise rather than natural phenomena. Noise as in airport radar, big, powerful airport radar. You can detect that if you've got a powerful enough receiver, you can detect that from far away. And so you'd look for signatures like that. And that's what our scientists are trying to do right now, trawling through huge amounts of data to look for the fingerprints of intelligent life around the million closest stars. That is one of the drivers, but there are many, many drivers to really using this artificial intelligence revolution to sift through the data in very smart ways that allow us to make new discoveries. This really is quite a transformational time for us the combination of much bigger instruments spewing out a lot more data with far more sophisticated tools to be able to search through this. It's a very, very exciting discovery time. This is my PhD supervisor at Oxford, Steve Rawlings, who was a key part of not only the Square Kilometre Array Observatory, but also about MeerKAT being established here, and MeerKAT being as big as it is. He used to say to Justin Jonas in the room, they were very good friends and worked closely together, build it well, and they will come. And he was speaking about the international scientists around the world. But I think what's been a transformational aspect around the MeerKAT is just how incredibly inspiring it has been for young, bright minds to get involved on the technology, on the science that's to be done with this. This is a picture from our annual conference, from the South African Radio Astronomy Observatory conference, rather. And this is all of us, but it's majority students and postdocs, postgraduate students and postdocs. And they are leading a lot of the discoveries that you're reading, that you may be reading in the news. And it's really fantastic to be working with these students and postdocs. So I run something called IDIA, Institute of Astronomy. One of our main missions is providing the compute infrastructure. We run a data center effectively to do a lot of the science and to facilitate a lot of those students being able to do their work. That's done the wrong thing. I can show videos later. That started at the wrong point, but let me break there for questions, please. One straight away.
Comment first, and then I'll ask the question. So my comment is, and don't stop. I mean, this is just the best thing I've ever heard. Well done. This is absolutely superb. It's entertaining. It's teaching me so much. You've got such brilliant images, and you explained it all so well that I can't say enough. So well,
it's very kind of you.
Absolutely blew my mind. The question is, we've all spoken about the universe. Now I read that there's a multiverse, that we've stopped this idea of something that's finite. So is the multiverse infinity? And if there's infinity, are there not as many Earths just like ours out there over and over again?
Roger, can I ask you to repeat the question so it can be recorded?
Sure. So the question is centered around whether there is not, in fact, a multiverse rather than a universe, multiple universes. And if so, well, the number of Earth-like planets could be infinite. So yes, there's a whole lot of research going into whether, in fact, there is a multiverse or not. It's very difficult to get observational evidence. And as you may have picked up, I'm an astronomer who likes data. I like observing and getting light from a thing or gravitational waves from a thing that I want to study. Where the multiverse gets very difficult to do is to actually prove that it exists observationally. There are some ideas about that. And in fact, I once asked in an interview, what's the observational evidence for that we live in a multiverse? But it's very difficult to do. One of the pieces of evidence is that we might see massive circles in the afterglow of the Big Bang. And that's something that has been searched for, and there is no evidence of that yet. However, there are very strong theoretical reasons that suggest that this is a very likely possibility. I don't want to get outside of my wheelhouse and go into the theoretical models because, frankly, I'm not clued up enough on them. But I don't think one needs to go to the multiverse to really see that clearly there are just maybe not infinite, but innumerable Earth-like planets. In fact, if you remember that, just looking across all those stars, we now know that pretty much every one of those stars, at least the average ones, which is the vast majority of them, has pretty much an Earth-like planet. That has been a revolution in astronomy in the last 25 years. I mean, the first extrasolar planet was discovered in 1995. There was a Nobel Prize given for it. Since then, there have been spacecraft that have gone up and measured and discovered thousands upon thousands of planets. And the statistics are such that you can just say, okay, with almost certainty, pretty much every average star has an Earth-like planet. It's just a question of which ones we can detect. So I think maybe the next step to your question is, surely there's life everywhere. I don't have observational evidence for you. We don't have that yet. But although there were some interesting videos released by CNN recently on this topic, I find it hard to believe that the universe isn't teeming with life. Yeah, let alone our own galaxy. So yeah.
It seems to me possibly that black holes could be the opening of a wormhole, and that all the stuff going into the black hole disappears. And they could come out in another universe, and maybe there are as many universes as black holes. Yes. In which case, then, as soon as you've moved out of our particular field of view, you're in another universe straight away. And so, in that universe, you could be married to my wife, and I could be a bachelor. In other words, there's two sets of all, okay, doing all different things.
Yeah.
Okay. But what worries me about black holes is, if you look at what's happening there, everything goes into the black hole. And if you look at a black hole like the plug in your sink, the water goes down there, all right, and then it disappears, but it doesn't really. It goes down a whole lot of parts, end up in your septic tank, which is another universe. Okay? So basically, I think that's the same thing that's happening in space, because it's an analogy which makes sense to me in terms of practical.
I mean, the sort of, there's something called the information paradox. Things disappear into black holes. So firstly, you've got to survive spaghettification. Forces are so different that your body just gets ripped apart if you enter into a black hole as a human. But stuff that goes in, there's this paradox. Hawking said that the information retained or not? Is it just kind of, is that lost to the universe forever? And there are a whole lot of theories. Firstly, just on the boundary of the black hole, is that information about what went in retained in some way? Then there's the question of what happens on the other side of the boundary of the black hole, the so-called event horizon. And yes, it could be a white hole where things just go out on the other end. We don't know. We can't get information from behind the event horizon. So it goes to the multiverse question as well. There are elegant theories about what lies behind and what the nature of black holes is, and whether that's connected to even the universe's accelerated expansion, dark energy. But we don't have data. So it's very difficult to compare what is and, elegant theories. There are more and more novel ideas about how to go about this, but at the moment, there are far more theories than there are credible data points.
Right. To go one stage further, we can see the black holes which are end onto us like that. We can see the black spot in the middle.
What do you mean end? Oh, so the accretion flow is
Yeah. Right. So in other words, it's flat onto it.
Mm.
Okay. But what if it happens to be sideways? Then you won't see the black hole.
Look the same.
You will see maybe some gas and stream coming out this side, and then all of a sudden it disappears.
So you can actually see it because they bend gravity so much, but it'll have the accretion flow. What's in front of it? I've got a slide in fact, I think I probably showed it in that previous presentation I gave to this group. It's a bit like look at Saturn with the rings edge on. You see a line that just goes in front of Saturn. I'll remove Saturn, put the black hole there. If you look at Saturn in another way, from top down, you see the rings. Black holes combine that view. You see the rings bent over it and under it, and you see the ring in front of it. So you still see the black hole if you've got a powerful enough telescope.
I want to make a comment and then a question. Just the comment is that the Advanced Astronomy Center actually visited Carnarvon just as CAT 7 was being completed. The design team was actually there. The second comment is that we were the first group to visit MeerKAT 2 weeks after its completion, and that specific image it was donated as a memento to the Advanced Astronomy Center.
Wow.
A color picture. I think it's in copper base, which is pretty special.
Yeah.
So we've been aware of that.
Wow.
My question is that you came at least, I think, to common prominence with the Event Horizon photograph and the large role that South African scientists played in the data processing. Now, when did you get involved with MeerKAT's data processing? Which came first, MeerKAT or Event Horizon? Simple question.
Yeah. So I'll try and as short a story as possible. So my interests have always been in these global networks and more compact telescopes like MeerKAT. MeerKAT only switched on, as you know, you were there 2 weeks after it was July 2018. So you probably were there in August, early August. So the country was gearing up towards that moment where it would switch on, and we're trying to train people up to be ready for when the data comes through, because it really was it's a huge step going from traditional data sets that we're dealing with pre-2018 to what MeerKAT steps up. So a lot of what we were doing there was creating fake data sets synthesized in a computer and being ready, putting as realistic a thing as possible. So I was doing that for MeerKAT, but I quickly realized I was lucky enough to attend an Event Horizon Telescope collaboration meeting because of some other black hole research that I was doing, and I saw that there was a gap. They didn't have that key part of the data processing in there to generate fake data sets as realistic as possible. So I love the telescope. I love the idea. I love the sort of complete shot in the dark. It was no one thought we were actually going to pull it off. I love that aspect, and I wanted to be a part of it, and I offered to be able to contribute that technical component to it in order to be part of the science. And fortunately, it was just lucky timing, and I had a few good postdocs and students that helped me build that software. And as part of that, we've done a whole lot of other things to end that sort of trajectory. My focus is, and my role at WITS was about training students up on MeerKAT and preparing them for SKA. So my research was, 95% on that. But I still have retained a couple of, in fact, one PhD student got his PhD was approved 2 days ago on some Event Horizon Telescope. And one of the things I've been doing in the background is motivating that we have a node in South Africa. We're looking at a few possible sites, including the Drakensberg and including Sutherland, where we can put one of those specialist designed nodes and continue a lot more actively continue our participation in the Event Horizon Telescope.
Nearly hear everything, but I'll still answer 2 questions. Did MeerKAT find the black hole at the center of our galaxy?
So that black hole was known back in the 70s that there was a supermassive black hole that lay. Well, it was a strong candidate. Then it was definitively shown. In fact, there was a Nobel Prize for this a few years ago. The infrared telescope zoomed in and saw stars doing this around nothing, and from that, that was the strongest evidence ever that there was a supermassive black hole. This came after that with a global network of telescopes, not with MeerKAT. What MeerKAT has done is look at this view of that, which is the much larger field of view of the phenomena that's going on. You can't see it in this, but the image is actually much bigger, and it's traced a big outflow of material up and down outside of the screen. And these filaments is what it's so precisely mapped and discovered. There were sort of 2 that were definitively known. It's mapped, I think, about 100 and traced the event that actually has lit them up. Yeah, I should think of a good analogy for them, but they're almost like these temporary sparklers that exist, but they need to be lit up to see, and they're lit up at the same time. Yeah, so that sorry if that was not quite clear.
Taken by MeerKAT.
Yeah.
That center is where the black hole would be if we could look at it end on.
Yeah. Well, that's where it is if we could see it with sharp enough view. It's blurred out, the central pixel here where that black hole lies. You still have to zoom in 1,000 times. Well, no, you still have to zoom in about 100,000 times into that central pixel to see the black hole. And you have to do it at a different wavelength of light. You wouldn't be able to see the black hole with this wavelength. Different science goals, yeah.
Well, it's nothing to do with astronomy, but I looked at the map once, and I wanted to go and visit the MeerKAT, and I saw it was part of the national park, so there's a national park around it, and I saw it had a gate, but I couldn't get any further. Can one visit it?
You can. You'll have to monitor the SRAO, South African Radio Astronomy Observatory website, sarao.ac.za. They announce public visits from time to time. They try and do about 2 a year. Unfortunately not, because even your camera will, exert some, release some, what's called radio frequency interference. And the sensors, the receivers on these antennas are so sensitive that they have to basically cover them up with special material to protect them when the public does come. But if you look out on their social media channels, every now and again, it's hard to predict. They haven't got into a mode where they can definitively say these are the dates. And when they announce it, tickets go up fast, and you've got to get yourself there. And yeah, it's a bit sad that it's not more valuable.
Would it be true to say that MeerKAT is the core of SKA, and that as you move out in a sort of logarithmic spiral, you end up going to Madagascar, East Africa, West Africa?
Yes. So so MeerKAT will be the core. There are a few more antennas that are going to be spread in amongst the core to densify the core a little bit more, and then it'll go out to about 40 kilometers. There'll be one antenna about 120 kilometers, but that's more for future engineering tests. And then using this global network I showed you, that spinning globe with the baselines, that'll connect up to antennas. There's going to be one in Botswana, and the ambition is to have more in Namibia, in Madagascar, in Mauritius. And if you look at the shape of that, the attempt there is to make a logarithmic spiral, because that makes the best images, effectively.
Now, the reason why you use a logarithmic spiral and not a circular spiral is because you want differing wavelengths with differing bases. So each one is longer and longer and longer.
Yeah.
So we've got so I would say that the difference between the bases, in other words, the bigger the base, the more precise the information.
Precisely.
And the smaller the base, the more general it is. So you get a sort of multispectral view of what you're looking at. So the stuff in the middle will give you the general shape, and the stuff on the outside will give you the detail.
Yes, multispatial. It's a bit like having an electron microscope for the very long, the antennas that are very far apart, and having your binoculars for birding with the compact core. You kind of need them both. Well, maybe not electron microscope and binoculars, but something closer. You want them both to kind of find things and map out the universe. And then when you really want to go deep and map a black hole, you go with the electron microscope. So that's the mix.
So if you take it further now, and you look at those metal jobbies in the desert in Australia, where do they fit into our design? Because if Africa was big enough, we'd put them all here, wouldn't we?
It's a separate telescope. It's a completely separate telescope. Tunes into a different radio station with its different set of scientific objectives. That's the telescope that's going to look at those cosmic dark ages. And so the design is completely separate. That's why they could come to a diplomatic solution, because they knew they were going to have to buy am I being too diplomatic? We needed to make sure that we were going to have to build two technologies anyway. So the site decision essentially decided, well, the easy solution here is just build one technology in South Africa and one.
If we have built the majority of MeerKAT in South Africa, I assume, then are we going to build the other copies of that and then export them to the place where they're going to be installed? Or are they going to be built separately to?
No, I mean, South Africa's contribution is the antennas in South Africa and the MeerKAT antennas, which are part of our contribution to the SKA. All those countries are contributing to the costs of the entire SKA Observatory. And we are handing over those antennas towards the end of the decade to the SKA Observatory. And then we get access to the Australian experiment, which a lot of our scientists are interested in, for example. So it's part of our contribution. But
So we're only paying for the stuff here. The other guys are paying for the road.
Well, we are contributing to the Square Kilometre Array Observatory, which is a global collaboration to deliver these telescopes. Our contribution is what we built here locally.
So two questions. What is the estimated date of completion of SKA, and are there any speed bump, financial or otherwise, on the way there? And the second question, how much data, can you give us a figure, how much data has been collected so far from MeerKAT, and how much of that is still to be analyzed and prepared for? Is it all analyzed straight away?
Yeah, these are good questions. So the first part of the low frequency telescope in Australia, it's a lot simpler to operate in its first phase, and that'll come online 2029. 2031 is when we expect kind of the first light science operations with the SKAO in South Africa. MeerKAT will continue up until about 2029, 2030. There is an engineering transition there that needs to happen. Data rates are huge. This is about a terabyte per hour. You tally that up, it's petabyte territory per year. The data center we run is not meant to store all the data at all. It's meant to be there for the data processing. And then when you're done, you move it off, you delete it. And we have 14 petabytes of storage. MeerKAT archive at the moment is of order about, I think it's about 80 petabytes. They have to move stuff off to disk, to these disks. They can't keep them on running computers because of the challenge. And then SKO will be about an order of magnitude larger. The very interesting question you ask there, one of the very interesting questions you ask there is, how much of the data has actually been analyzed? And that is it kind of keeps me up at night a little bit on what discoveries lie on disk that we haven't made yet. We just need to, get enough compute and get enough talented people to have eyes on and ask the right questions of the data. And so that is part of our formulation of really trying to equip ourselves as much as possible to make those discoveries and make sure that we're looking at all the data. We're trying to tackle this in a very holistic way, because you can slice and dice the data in many different ways. You can make movies and snapshot the data every 8 seconds if you wish. But that's expensive. You can slice it up in those colors, the 32,000 colors, or you can average them together. So we've got to make trade-offs, and we've got to be guided by the scientific intuition, I guess, and by theories that say what we might see with the following description. So there's an interesting mix of technical competency and the scientific know-how to go about it.
I assume there's a lot of processing with supercomputers and
Yeah, I mean our data center is a hefty data center, and it's chock-a-block full because we've got 600 users that are wanting to find out what discoveries lie in their data.
You did mention AI. How would that assist you in that examination of the data?
Yeah, so in multiple ways. I mean, the most immediate way that it's really transformed astronomy is with the coding. Every astronomer has to do a whole lot of programming in order to interact with their data and change calibrate the data, try and bring those musical notes into focus. So there's a lot of work around that, and AI just helps you code much better. A graduate student can suddenly say, "Hey, help me code up the following thing," and there's not always, but there is pretty professional code. You've got to interact with it because it does get stuff wrong, make no mistake. It can also help someone like me who's spending far too much time on email and not enough time on code anymore and research, get up to speed on the latest. So that is the most kind of key way it's helping at the moment. But there are ways a key problem we have in astronomy, for example, is finding the needle in the haystack. There's an interesting object out there, but there are a million dots. How do you find it? You can get 100 graduate students to search through that, or you can get some clever algorithm that is able to process that, whether it's a convolutional neural network or increasingly there's use of LLMs, find the interesting thing. And it's very, very proficient at that. And because we're spewing out these huge amounts of data, we are actually having to use AI. It's not it can't be a buzzword anymore. It's becoming an essential ingredient in modern astronomy.
This is a stupid question, but aren't you worried about being replaced by AI?
Oh, yeah.
there is a question from Ian. You mentioned that MeerKAT can detect gravitational waves. On these correlated check against LIGO.
So that's a good question. So the question was, MeerKAT can detect gravitational waves. LIGO is an experiment. Well, there are two arms of it in the US, and it uses laser beams to also detect gravitational waves. And it won a Nobel Prize back in 2015 for the first detection of gravitational waves. What it detects are much lighter objects spiraling into each other in a similar way to what you saw me present earlier. Those are neutron stars, those city-sized stars that spiral in. And when they do that, they distort the space-time. But the pitch is a lot higher than the pitch of the gravitational waves that MeerKAT detects. So there is a whole, just like the electromagnetic spectrum goes from X-rays through to radio waves, and everything in between, including optical, and these have got different frequencies. Gravitational waves have different frequencies as well. So LIGO detects much higher frequencies because it's detecting different objects that can actually get closer together and become one. MeerKAT detects supermassive black holes that are solar system sized rather than city sized, and they merge with a much slower and the effective slow hum rather than this bright pitch. So they're giving complementary pieces of evidence of different astrophysical objects.
Can you give an idea of the difference in sensitivity between MeerKAT and LIGO? Is the LIGO signal it detects much fainter or not?
It's measured in something called strain. So if you think of a strain gauge on a bridge, when the army goes over, or a big vehicle, we'll be able to measure the squashing, the change in length. The strain of LIGO, I believe, is a few orders of magnitude smaller. And that's because it's using infrared lasers and interfering the light. So it can get a far more accurate measurement of the change in length. Whereas MeerKAT's using these clocks, but there are, these spinning neutron stars are spread across the galaxy. it's not quite as accurate. But in the same way, you know, MeerKAT's not as, yeah, it's not really I guess you can make a head-to-head comparison, but because they're tracing different physical phenomena, it's not as apples and apples to comparison, I don't think.
All right, thank you very much. This was as brilliant as expected from you.
Sure.
We enjoyed that hugely. Thank you very much for your effort that you put into that.
No, my pleasure.
Great.
Thanks a
Thank you
lot.
very much.
Thanks for coming, everyone.
Thank you.